The idea of the method of superposition is that we can add tabulated solutions to obtain solutions for more complicated cases. In other words, a complicated load could be split into several simple loads for which the solutions are available. So for this purpose, we need to have a table of simple solutions. So we will be using two tables. The first table is for the cantilever beam with uniform stiffness, and the length of the beam is L, and we have tabulations for the deflection line as a function of x, its derivative or the slope, and the values of v and v prime at the tip. So here's a typical table. Here 1 says that this is table 1, right? So I'll have about a dozen or so tables like this. And here's V that I copied here. And first, I want to check the consistency of this table. In other words, I would like to evaluate V at x equal to L. And of course, this must be consistent with delta B, the displacement at the tip, and it is. I can do actually more. I can take V, differentiate it twice, and calculate the bending moment. And I get a quadratic function, which is consistent with the bending moment diagram, of course, and observe that at x equal to 0, the value of the bending moment is minus half QL squared, which could be easily established by drawing the free body diagram for the entire beam. And at x equal to L, it is 0, and indeed that's true because there are no couples applied at the tip. Now, I can do pretty much the same with the shear force. Again, get the expected linear function, which gives me QL, or the force up, at the left end, and 0 force at the right end, and both of them are consistent with equilibrium. The other set of tables I have are for simply supported beam. They're a little bit more elaborate because they have the displacement in the midpoint, delta C, and the maximum displacement, and of course we have two interesting angles, both at A and B. And here is a typical entry. This is entry number 2. And so you can see that the displacement and slope are given by two functions each, one defined on the left part and the other on the right part. And this is natural because the load changes from uniform to 0. And we also have the values of delta C and theta A and theta B. What is missing in this table is delta max. It's just not given. And so I would like to use this table to calculate what is delta max. You see here in the description of the beam, it is promised, but it's not delivered. So let us figure out what is delta max. To do, I will assume that delta max lives somewhere here between 0 and L over 2. That's a reasonable assumption. And with this assumption, it means that I will be working with these two functions, V and V prime. And so I will first copy them. And now I say the following. To find the maximum deflection, I will set the derivative v prime to 0. And this gives me the following quadratic cubic equation, which is, of course, exactly this equation, right? And now to solve it, I'll make an obvious substitution. I will introduce psi, and psi is x over L. And what this does, it replaces this equation, which has the parameter L, with this equation, which doesn't have any parameters. And I end up with 3 roots. I solve this equation numerically. If I look at this root is clearly unacceptable because it says that the maximum is somewhere here. I even don't have a beam here. This root implies that the maximum is at 0.978 L, which means it is here. But my equation is valid only from 0 to L over 2, so this is outside the interval. The only root that is inside the interval is this one, and therefore I choose it as the location of the point where V is max, and this location is, of course, obtained by multiplying psi2 by L. And now all I have to do is take this value of L and substitute it in here, and this will give me V max, and the value is given here. So let us look at a very basic example problem. So in this case, we have a cantilever beam loaded by a force P and a couple PL, and our task is to find the deflection of the tip. So this case is typical for simple problems because we have here 2 loads. And what I want to do, I want to use the tables for each load and then sum together the displacement induced by each load to get the displacement due to the combined load. So the first table is table 4, and it gives the deflection as a function of x for this beam. And the second table is for a beam loaded by a couple somewhere in the middle. It's table 7. And now let me use this expression evaluated at x equal to L, because I'm interested at the deflection of the tip. So I end up with PL cube over 3I. And for the second loading, I take this expression because I'm interested in the location here, and this is clearly this branch of the solution, right? To the right of the applied couple. So I put x equal to L because I'm interested at the deflection at the tip. My A is equal to L over 2, and M naught is equal to minus PL. The reason is that my moment is counterclockwise. The moment used here is clockwise. So I put minus PL, and as a result, I obtain this value for the displacement. Now, all I have to do is to add this value and this value, and I obtain this result, which means that the tip goes up And the reason for it going up is that despite the fact that the force pushes it down, the couple lifts it, and the couple apparently has an upper hand in this situation. So let's also say that this problem could be solved simpler. I could use now extended table where I have delta B, or the displacement of the tip that has been tabulated for me. I do the same for the second case, right? I have two expressions, and now V of L, I just simply copy this result, and V of L here, I copy this result by plugging in A equal to L over 2, and again, M naught is minus PL, and of course I get the same answer as before. And so this shows us that there are multiple ways of using the tables, and of course there are multiple ways of generating the tables. Some tables are more complete than others. Let us look at a problem which is a little bit trickier. So my problem here involves a simply supported beam loaded by a force P somewhere in the middle. A and B are given. Their sum is, of course, L. And I am interested in computing the deflection at a point in the middle of the right span. So at A plus B over 2. Now, there is a table. It's table 5, which looks perfect at first. But then I realized that the only entry in this table is for x between 0 and 8. So for this segment of the beam. But I want my x to be here. So to deal with this issue, I would like still to use this table, but I need a tiny. So let me begin with the original beam. And now what I will do, I will look at the same beam, but loaded slightly different. So what happens? Now the force P is located at a distance B from the left and A from the right. And the point of interest is now here, so to the left of the force. You may think about generating this beam by simply rotating the original beam 180 degrees about the vertical axis, some kind of mirror imaging, right? And now let's see what happens if I want to deal with this beam. I take the same table, right? And now I have the tabulated solution for the left part of the beam, which I certainly like because the point is on the left. But now I have to adopt this result for this beam. And now I can see that the difference between the tabulated beam and this beam is A and B are switched. So I take this solution and I replace B with A, B with A, and A with B. And that's what I have, right? And this solution is valid between 0 and B, or on the left segment of the beam. Now, this solution is ideal for me because all I have to do is to evaluate it at x equal to B over 2, and this gives me the desired result.